So now we're going to look at measuring enthalpy changes for chemical reactions. And as I said before, we'll be talking about the use of the calorimeters when it comes to doing these sort of measurements. So I mentioned this before, and I'm going to say it here again. If you have a reaction that is carried out in a calorimeter, any heat that is evolved by the reaction is going to be absorbed by the calorimeter and its contents, all right? So that's why we can write down this equation as a relationship between the heat change for the reaction and the heat change for the calorimeter. Whatever the amount of heat that is released in the reaction, that would be equal to the amount of heat that is absorbed by the calorimeter. And of course, that's because, the calorimeter is designed so that no heat change will take place or heat exchange will take place between the inside of the calorimeter and the surroundings. So, since we know that this is the relationship or the equation we can use to calculate the heat change of the calorimeter, all we have to do is put a negative sign in front of the resulting answer here, and that will give us the Q of the reaction, right? So basically, the way we use the calorimeter to measure the heat change or the heat of a reaction is that we basically need to know the mass of the contents of the calorimeter, we need to know the specific heat, and we need to measure the temperature change, all right? So these are the three things that we're going to need in order to determine the heat that is absorbed by the calorimeter, and in so doing, we can determine the heat change for the reaction itself. So with that said, let's look at these two examples. And I'm going to start off with the first one. So in the case of the first one, they gave us some information about a 0.250 molar solution of hydrochloric acid. Its temperature initially is 19.50 degrees, and the volume is given as 50.00 mils, and it's added to an equal amount of sodium hydroxide of the same molarity and the same temperature in a calorimeter. It says after mixing, the solution temperature rises to 21.21 degrees Celsius, and the question is asking you to calculate the specific heat, the heat of this reaction, and we're to assume that the specific heat of the resulting solution is the same as that of water. Okay, so let me get out of this here and go to my writing pad here. Let me clean this up. And what I'm going to do is determine the mass of, how should I put this now? Let me see. They gave you the volume, they gave you the molarity, and they gave you, so what we can find is the moles of each component. So the moles of HCl that we're going to calculate will be equal to the moles of sodium hydroxide, because the volume and the molarity are the same, and that would be equal to 50.0 mils. We convert that to liters, so 1 liter above, 1,000 mils below, and then we multiply that by the molarity in the form of this conversion factor, 0.250 moles divided by 1 liter. All right, so these units will cancel out, and we're going to end up with, let's see here, 50 divided by 1,000 times 0.250. So according to my calculation, the moles of both sodium hydroxide and hydrochloric acid would be 0.0125 moles. All right. The next thing we're going to find is the mass of the solution. Now, we have to make an assumption here. The mass of the solution will be equal to the density, would be equal to the density multiplied by the volume, all right? Now, the volume, the total volume of the solution, let me write this down, will be the 50 mils of the sodium hydroxide plus the 50 mils of the hydrochloric acid. So that will be a total of 100.0 mils, all right? Now, another assumption that we have to make here is that the density of the solution will be the same as the density of water. So 1.00 grams per mil would be the density, and we multiply that by the volume given, which is 100.0 mils. So that's going to be equal to 100 grams, all right? So that would be the mass of the solution. So Q is going to be equal to the mass of the solution times the specific heat times the change in temperature. Now, the mass we calculated to be 100 grams. The specific heat, we assume that to be 4.184. I'm just going to run it to 4.18 joules over gram degree Celsius. And then we get to the temperature change. And if you look at the question says that the final temperature is 21.21 degrees Celsius. And the initial temperature for both solutions was 19.50 degrees Celsius. And we have to work this out. Of course, we work out what's in the parentheses first. 21.20 minus 19.50 gives 1.7 degrees Celsius. So I'm going to put 1.7 degrees Celsius here. And then multiply that by 4.18 times 100. And round it off to 2 sig figs. So that gives us 710 joules. So that would be the heat change for this reaction, the heat of this reaction. All right. So that answers the first part. So let me go back to the PowerPoint here. That answers this question here. So now we have to look at let me see here. Now we have to look at answering this question, which is based on the first question. The question says express the result of the previous question for molar amounts of reactants and products. That is, determine the value of delta H that should be written in the equation for the neutralization reaction, and they gave you the reaction equation. So if you look at this equation, it's a 1-to-1 mole ratio between the hydrochloric acid and the sodium hydroxide, right? So basically what this question is asking for you to do is to determine the heat change when 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. Based on what we have done so far, we have determined that the mole of hydrochloric acid and sodium hydroxide is 0.125 moles. So therefore, for one mole of either HCl or sodium hydroxide, then delta H would be equal to what we calculated here, 710 joules, which is for 0.125 moles, but we have to divide that by 0.10125 moles to get the answer that the question is asking for. So 710 divided by 0.0125, and according to my calculation, this is equal to 5.7 times 10 to the 4 joules per mole, which would be the same thing as 57 kilojoules per mole. All right, so that's basically how we answer this question. All right, okay, I'm going to stop here for this video, and the next topic that we'll be dealing with is we're going to talk about bomb calorimetry. We won't spend too much time talking about it. I don't think we'll be doing any calculations involving bomb. So what I really want to get to is this law here, Hess's law. So this will be basically the bulk of the next video. All right. Okay. Until next time.